there are like two sublattices of niobium in SVN, and then niobium 1 is always shifting along C, and niobium 2 just shifts at low temperature. So this is the guy who is really contributing to the ferroelectricity. And now this is my last slide. You see that you can calculate an average of the deviation of the niobium along C. Here I average 8 cells, 8 octahedra, and some of these octahedra, the special ones, they are fixed at all the temperatures. So you see here that darker blue and darker red are the maximum deviations of the polarization of the shift, and they are even at high temperatures. So these atoms are all the time shifted, so it's a kind of built-in polarization in the structure, and the network of the perovskite octahedra, they change the color because at high temperature the polarization is dynamic, so niobium is flipping, or sometimes it's in the middle, sometimes it's more shifted or less, and then when you lower the temperature, they start to coordinate, let's say, to correlate, and at some point niobiums freeze, and then you have some up and some down, and you can have something like, let's say, domains or artificial domains here, this theoretical construction. But this is just to show you that it's important to see this interlay of two networks of niobium and octahedra, and this is somehow contributing to the picture of the change from ferroelectric to relaxor behavior, according to this second sublattice. And with this, yes, I will go to the summary, and I will just remind you two things from the microscopic view. The most important thing in SVN is that you have multiple mechanisms for the polarizations, and for the microscopic view is that the octahedral tilting is something inherent in the structure. It doesn't per se contribute to the polarization, but somehow influence the relaxor ferroelectric behavior due to this coexistence of two sublattices in niobium. So with this, I will finish, and then I thank you for your attention.
So we're technically over time, but I think we have time for one question. One question.
I can ask again. That's really interesting. This relaxor field. So this microwave frequency, you fit the microwave relaxation. You fit with cold. So I have two questions for you.
Yes.
What is the alpha you got? And can you fit with the HN model? And if you fit with HN model, will it change a lot the results or not?
You asked about the alpha?
Yeah.
Oh, no, I forgot the data, but of course alpha is changing with the temperature, and it's going higher, with low temperatures. Now I don't remember, but maybe it can be 0.2 at very high temperatures, or almost divide at high temperatures, or maybe 0.78 at the lowest temperature, when you have much wider contribution.
I think we really should probably wrap up and continue the questions in the hallway, because we have one more session. But let's this afternoon. But let's thank all the speakers.